Hi AP Environmental Science students. Welcome to this lecture on soil composition and properties of soil. So for the learning objective, we are in topic 4.3, soil composition and properties. With the learning objective, describe similarities and differences between properties of different soil types. And again, we'll talk about the essential knowledge at the end, as usual. The vocab is here. You can pause this now to jot it down, but there isn't much. So starting with soil composition, we talked a lot about soil composition in the last PowerPoint when we talked about how soils are made, specifically how they are broken down and the factors that influence how they're broken down, such as topography, climate, and biological factors, but we talked a lot about this last time. So soil is primarily made of broken down parent material. This is also what we would call inorganic sediment. That's basically your sands, silts, clays, pebbles that are in that soil. It also tends to have organic matter in it, or it may be completely absent in organic matter. So like the sands of the Sahara may be completely absent of organic matter. There might be a little bit in this cracked clay that looks like some grasses are trying to grow up into it, and then there's going to be a ton of organic matter in this field on the bottom right. Remember that dark soils are the best because they are high in organic matter, and organic matter is going to support all of the microorganisms, all the beneficial microorganisms, and even macroorganisms like earthworms in your soil. Recall that soils also have gases trapped in the matrix of the soil, the three-dimensional matrix. There should be atmospheric air in that soil, right? Oxygen most notably. And then liquids, those liquids mostly being water, and then the organisms that live in the soil that call it home. The relative amounts of these are going to vary greatly, like I just discussed. So diving a little bit more into sediment. So sediments are going to be classified based off the grain size, and you see this is just copied and pasted off of Wikipedia, the different grain sizes. We are only interested in sand, silt, and clay. So we're only interested in these ones right here. But realistically, all of these sands we're going to group together. We're just interested in sand, silt, and clay for this class. All of the other ones are important, but maybe not so for this class. Okay. We are also interested in humus, which is the organic matter in the soil, or at least we're going to call organic matter in the soil. We're going to call all organic matter in the soil in this class humus, just to simplify things. Okay. And the different sediment types are going to determine the texture of that soil. So how that soil feels, and that will give it some of its different properties. So if we break those sediments down again into sands, silts, and clays, those different sediments are going to give those soils different properties. If soil is high in sand, it's going to typically have large pore sizes, meaning large gaps between the pieces of sand, right? So we're talking about rock, it's very coarse, and we have 3 grains of sand right here, and there is this big air gap right there. It also is going to allow water to drain really easily because it's going to go through all of the nooks and crannies between those sand particles. So there's going to be low water retention. And because there's going to be low water retention, there's going to be high drainage. Those two are going to be inversely related to one another. Okay. Silts, those are our medium size. So sands are our large size grains. Silt is our medium size grain. Typically will be deposited by rivers, and it forms fertile soils and floodplains. So silts will be carried by the river, and it's typically what you see in a really murky river will be a lot of silt content. Right? They have high water retention and medium drainage, so they're actually really, really good for growing plants because they hold enough water to grow your plants, but they have enough drainage so that those plants don't get waterlogged. However, if they do get waterlogged, that can often happen, especially because they tend to be in floodplains. So if the river does flood and if it stays at a high water mark for long enough, it can become waterlogged. Okay. Clays, those are our smallest grain size, or at least the smallest grain size that we'll talk about in this class. They can form hard pan clays, meaning that it's just like a baked layer of clay. Think about like a clay pot. Not much water is going to go through that, and it's not going to absorb water very easily. Okay, so it's just compressed clays, and it's sometimes formed in very hot areas, so it's almost kind of like it's baked. Okay. Um, and these small grain size lead to small pores, and those small pores actually can hold water too well. So there's the amount of force that plants can draw water out of a soil, but water will stick to clays beyond that force that the plant roots can pull it out, and that's called hygroscopic action. And they basically, those clays will hold onto the water stronger than plants can absorb it. So there might be a tiny amount of water in that soil, but your plants are going to wilt, wither, and die because they can't take that water away from the clay. So that's one of the big problems with clays, especially in arid environments. So just reiterating a lot of that on the right and then with the pictures. So sand has the largest grain sizes and water can easily flow all through this. And you guys know, being on the beach and seeing how water interacts with sand, that it does not hold water very easily. In fact, it drains almost too well for most plants. All right, silt, you still have a lot of air pockets, you still have a lot of oxygen in those soils, and water can make its way through, and it does make its way through. It has medium drainage, but it has enough water retention to grow plants pretty well. And then clays. Clays can pack down like little bricks, like it shows in this diagram. They're super, super small, and they can compact very tightly. So if water gets on here, there's no space for it to go through. Maybe it'll go to like this section, but there's no space for it to go through. So it will instead run off, and it will run off sideways on the surface of the soil, right? Or it will pool on the top and only infiltrate the soil after a very long time, or a relatively long time, right? And again, if water does get down here, it can become bound to this clay molecule. And it can become bound so strongly that plants, if there's so little water, that water will be attracted to the clay so much that plants can't take it away. Okay, so clays are typically what we would characterize as the worst soils. They compact down, they form hard pans, and they don't absorb water very well. And when they do absorb water, they hold it almost too tightly for plants to take that water away and to absorb. The best soil type, though, is neither pure sand, pure silt, or pure clay. It is loam. And loam is a mixture of sand, silt, and clay, and it displays the best characteristics of each. So it's about 40% sand, about 40% silt, and about 20% clay. So you have the drainage action of sand, you have the large pores that sand provides for the soil type, so you have a lot of oxygen and other gases in that soil. And again, you have enough drainage. You have the silt, which is the happy medium between clay and sand, so it holds that water pretty well. It also drains pretty well, and it also allows oxygen to get down into the soil. And then you have clay, and just enough clay to allow pretty good water retention, because that clay will hold on to water for a pretty long period of time, but not enough clay to be compacted down into a hard layer, because it's going to be broken up by the sand and the silt. Okay. When you have a loamy soil, it's often going to be high in organic matter. And I don't know how many times, I can't stress this enough, I should say, whenever you see dark soils, you are going to have a very fertile soil, because it is high in organic matter. So organic matter is going to give you dark soil, which is going to be extremely fertile. And these loamy soils are typically high in organic matter because they're the best soil type, and you're going to have a lot of vegetation growing on there for centuries or thousands of years. Okay. So I mentioned drainage, I've mentioned water holding capacity a couple times. I want to define water holding capacity at least, because drainage is pretty simple, and drainage is essentially infiltration, and it's water flowing through that soil just down the soil column via gravity. But water holding capacity is basically how much water a soil can hold. It's its saturation point. So how much water that soil can hold. Think about a sponge. Think about your soil kind of like a sponge. There's only so much water that your kitchen sponge can absorb until it becomes saturated. It can't hold any more water, and any more water that you pour onto that sponge is just going to run off the surface, and that's the same thing that happens with soils. Okay, so it'll hold a certain amount of soil until it is saturated, until it can't hold anymore, and then water will either run off of the surface or just pool on the surface. And this is probably what you see after a heavy rainfall or a long sustained rainfall. Okay, and that's going to be linked with productivity. If you have very low, typically, if you have very low water holding capacity, you're not going to have a lot of water in that soil. It's going to drain too fast, and you're not going to have very many plants supported by that soil. Think about a desert sandy soil, right? It's going to have very low water holding capacity because it's mostly sand, and it's going to drain water too quickly. It's not going to rain very often because it's in the desert. It's going to drain water too quickly, and you're going to have low primary productivity, meaning low plants, low amount of photosynthesis. If we contrast that with like a deciduous forest where we have a really thick soil and it's often very silty, maybe sandy, very loamy in many cases, and you have a lot of organic matter is kind of like a sponge in that soil, which itself is kind of like a sponge. It's a sponge within a sponge. That organic matter is going to hold water very well. You're going to have a lot of, or a really high water holding capacity linked with a lot of productivity. Okay. But areas naturally do differ in rainfall. So we can have a very similar sandy soil in East Texas, where it is very boggy, versus West Texas, where it is very rainy. East Texas is getting a lot of rain. West Texas is very arid, not getting a lot of rain. And even though you have sandy soils in both, you're going to have higher productivity in, we'll say net primary productivity in East Texas and lower net primary productivity in West Texas, just because of the amount of precipitation. Okay. So in general, we're going to say that sandy soils drain very well and don't hold water. Clay and silty soils drain well and hold water. Silt is more productive than clay because clay tends to compact, and if it does compact, it's not going to absorb that water. But again, loam is the best. One of the tools that we can use to characterize different soil textures is the soil texture triangle. And you guys will need to know how to use this tool. It's relatively straightforward. There are three axes. On the left axis, you have clay. On the right axis, you have silt pointing down and to the right. And on the lower axis, the bottom axis, you have sand pointing to the left. Okay. Let's just say that you have a soil that is 35% clay, 25% silt, and 40% sand. What you would do is look at your clay. It doesn't matter which one you start with, but I'm going to look at clay first. It says 35% clay, so just moving from the bottom left to the top right, I'm going to find 35%, which is right about there. And then I'm given 25% silt, so 25% silt from the top left down to the bottom right, 25% silt and 40% sand, right? If I follow those three lines in, there's going to be a point where they all intersect. In fact, you only need two of the three because the third one is going to add up to 100%, and it should be right there in clay loam. Okay, so let me delete all of this and I'll have the nice animations come up, which will show how you do that. So again, looking at each one, what's the percentage? Following the line down or across or up, depending on which one you're looking at, and then where they intersect is the soil type that you have. So in the last PowerPoint, we talked about different soil horizons, and those soil horizons are going to have different different grain sizes, different textures. All right, even if it's the same broken down parent material, it's still going to have different textures and the different horizons, okay? So the O horizon is going to be primarily organic material, so it's not really going to have any sand, silts, or clays unless they get churned up or tilled up by biologic activity or even, tectonic activity, I guess, but mostly biologic activity. The A horizon is going to be high in organic matter because it's, filtering down from the O horizon and it's breaking down into the A horizon. And it's going to be variable particle size. That variable particle size is going to be different due to the location and the soil type, right? If we are in a loam, like if it's loam, it's going to be loam. If it's like a area where it's mostly flood deposits of silt, then it's going to be silt. If it's a sandy desert, then it's going to be sand, right? So we're talking about variable grain size based off of the different location and the climatic factors and the biological factors of that area, okay? And the geographic factors and all that stuff that we talked about last time. The E horizon is going to be kind of an extenuation of the A, but with all the good stuff, all the water-soluble nutrients leached out, but it's still going to be the same grain size as the A horizon, more or less. Typically more sand and silt, but also variable based off of the location and the soil type. The B horizon, though, is typically going to be high in clay. The reason for that is if you have your A horizon up here and you have, your large grain sizes of sands, right? They are going to allow very small particles. I'll do that in a different color, like purple. They're going to allow very small particles like clay to filter down between the nooks and crannies of the sand and go into the the B horizon. Okay, so the B horizon is going to be mostly clay because that clay, that small, fine clay, is going to get washed through the large pore sizes, the large hole spaces between the particles of sand. All right. The C horizon is going to have little, if any, organic matter. It's primarily going to be large pieces of broken down bedrock, so that'll be from pebbles up. So pebbles, rocks, boulders, whatever. It will also have material between those pebbles, between those rocks, between those boulders, and that will be mostly your clays, okay? Because the clay, again, is going to wash down through the soil column. And then the R is going to be solid bedrock. Besides texture and water holding capacity, a few other key aspects of soil that we could test for, and we will test for in class. Most of these are chemical, so these three right here are chemical tests or chemical characteristics of the soil. The first one being the nutrients that are available. So the macronutrients of N, P, and K. N is nitrogen. P is phosphorus. And K is potassium. Okay, so just the chemical symbols for those three elements. All right, we'll talk about this a lot more when we talk about land use and agriculture, but nitrogen is typically good for vegetative growth. Think shoots, so your stems and your leaves. Phosphorus is typically good for root growth, and potassium is typically good for fruit and flower. Okay, these are the things that plants need a lot of. They're the nutrients that they need in large amounts, so they're macronutrients. But there's also a lot of micronutrients, okay? Things that plants need a little bit of. So everything from calcium to magnesium to manganese to sulfur, any of these and many more plants need a little bit of, okay? And we could do tests to determine the relative concentrations of all of these, or the exact concentrations. We can do tests to determine pH, so whether it's neutral, acidic, or alkaline, soil contaminants or pollutants, and then this one is also a physical trait, just like soil texture, which is the stability. It's resistance to erosion. A lot of this we talked about last class with reducing erosion. So we talked about mulching and we talked about plant roots holding soil together, but there's also some stability in the soil itself that we can measure. Okay, this one we will not do in class. All of these tests are going to inform irrigation, fertilizing, construction, development choices, depending on what you're going to use that land for. Okay, so getting back to the learning objectives, we were talking about the similarities and differences between properties of different soil types. Again, those are mostly sand, silt, and clay, as well as loam. We talked about water holding capacity quite a bit, so the amount of water that the soil can hold, and that's going to vary depending on the soil type. All right, so sand is not going to have very good water holding capacity. Clay is going to have too much water holding capacity. Silt is kind of your happy medium. Loam is the best. All right, we talked a lot about the different particle sizes and the composition of each soil horizon, and those affect the porosity, the permeability, and the fertility of that soil. There's there's a variety of methods to test the chemical, physical, and biological properties of soil that can aid in a variety of decisions, such as irrigation and fertilization practices. This will mostly be covered in a couple labs in class. So we'll go back to that. And then the soil texture triangle. So you should be able to use a soil texture triangle and determine the percent, given the percentages of clay, silt, and sand. Given any two of those three variables, you should be able to figure out the third variable as well as the soil type.